All right, so last time we spent the time on these numerical problems where I am dealing with a large n. I want to break that problem up. Well, I decompose by going to a smaller n by, say, subtracting 1 or adding 1 to n. So today, the first thing I want to do is do some more concrete examples of this numerical stuff, just to show something that's actually running and how it actually works. And then the next thing we will do is go beyond just numerical problems and look at how some of the algorithms that we have looked at so far can actually be translated into recursion and often be more effective for the same reasons that we have discussed last time. So let's see if I can actually get this. So what's going on with the include? We'll deal with that in a sec. So the first thing we can do is just a simple example of something we did last time, like the factorial. What's going on here? Okay, finally. All right, so like we discussed last time, factorial, the only sort of end game, the termination condition for factorial is if n is equal to 0. And we can just do return 1 with factorial. For all other cases, you just get return n times factorial of n minus 1. Everyone remember that example from last time? Just something that actually calculates factorial. There are some minor, I would say, taste choices here that we make. So for example, in this case, I just put an if, I did not put an else. And it's actually worth talking about this just a little over here. So if you have n is equal to 0, return 1, else do this. This is one way of writing it. The reality is that if I actually remove the else, it's the exact same code. Because if the if statement was actually true, you are going to end up returning the value 1 regardless. So it's really a style thing. Different people would like to write it differently. I typically prefer the last statement to be more like outside any if or else. Just put it at the end. And again, it really is a style thing, but worth noting why I have that preference personally, because sometimes what I've seen happen is you have a code like looks like this, then you realize that there is perhaps a need for another termination condition, and you do n is greater than 0, and now all of a sudden we actually have a function that no longer has an exit when n is less than 0, and there's no assertion either. So sometimes what happens is you change a line of code, you end up with creating 2 return statements, but they both have a condition on them. If we did it this way, it's a little more explicit. It purely is a style thing. Technically, they're exactly the same. But just from a styling standpoint, this means that it's going to check the termination condition, and after that, it's going to decompose just right here. This is kind of the baseline case. It does not always apply, but where possible, I personally prefer to go like this. The else solution is equally good, and there's not really it's a religious debate. There isn't really much to it from a substance standpoint. And for us to actually run this function, I mean, it's really just a function that takes an integer argument. So we would get something like, if we say factorial 5, you can actually calculate this. Oh, let's just say So as we kind of expect, the hope is that when we'll run this, this will just take care of it. And what I'll probably do is just set up a once we've confirmed that it's working fine and compiles fine, then set up a breakpoint just to kind of take a look at what actually happens when this program is running. Ooh, you're right. So before it fails, we can go ahead and fix it. It is taking forever to compile. But what we can expect, and maybe before we actually do that, what we expect to see is factorial 5, first time we're going to run, n will be equal to 5, and we'll be breaking right here. And then every subsequent time, it'll be 1 less than that, so it'll be n is equal to 5, 4, 3, 2, 1. When n is equal to 0, you return 1. But then the interesting thing will begin to happen. You will actually say, we will have the returns start to happen. So the stack's going to grow. So we'll start with n is equal to 5 on the activation, then n is equal to 4, 3, 2, 1, 0. Then 0 will return, then 1 will return, then 2 will return, and so on and so forth. And it's actually worth noting that the calculation really happens kind of in the opposite order that the factorials are going to be called. So trying to avoid using the whiteboard since we're actually trying to do a video here. The idea is that factorial will get called in the orders start from factorial 5, factorial 4, factorial 3, factorial 2. The functions will actually start in the order with 5, 4, 3, 2, 1. But they will actually finish in the opposite order, and that's actually kind of an interesting thing to remember about recursion. The functions actually start in one order from 5, 4, 3, 2, 1, but the first function to return will be factorial 0, then factorial 1, then factorial 2, 3, 4, and 5. So what we want is to actually have a couple of breakpoints here, and let's run this again. All right, so as expected, n is equal to 5. The next thing that we'll see is n is equal to 4. I know that for you guys at the back, you can't really see, but just trust me, this is a 4 right here. And then as we keep hitting continue, we'll just see 3, 2, 1. With 1, we will actually see a call to factorial with n is equal to 0. So what I'm going to do is just add another breakpoint here. And now n is actually equal to 0. So the next continue would actually mean that the functions can start returning now and actually get their multiplications done. So factorial 0 returns first, then gets multiplied by returns to factorial 1, factorial 2. And as those functions return, the stack gets cleaned up. And what we finally get is the answer for 5 factorial, which is 120 in this case. So that's 5 times 4 times 3 times 2 times 1. The two things that are critical to remember is the order in which they could get called, 5, 4, 3, 2, 1, and then the opposite order in which they actually leave. Now, if we, like we discussed last time, recursion still in the numerical space can actually be of different kinds. So one of the things that we looked at was Fibonacci. The Fibonacci series, which is, we came up with a couple of termination conditions. And the answer, I believe in this case, is if it's 0 or 1, we'll actually do a return of 1. And otherwise, you'll actually do a Fibonacci of n minus 1 plus Fibonacci of n minus 2. Really just that simple a code. We just take care of the two termination conditions and we just specify the decomposition like we did last time. And let's try to get the element 5 of the Fibonacci series. So you have factorial, we're just going to be able to run Fibonacci. We'll do the same thing. Let's actually remove this breakpoint and the other two breakpoints that we set. Instead, we'll just set a breakpoint here and here. Again, nothing very different for the two, except in this case, it's a two-way recursion. Every function is leading to two function calls. Every call to fib is actually leading to two fib calls to other fibs for n-1 and n-2. Like we discussed last time, this does actually imply that we will see a lot of repetition that will be happening. So as n will be reduced, we will actually see n is equal to 4 coming up more than once, n is equal to 3 coming up more than once, and so on and so forth. So let's do that. Let's go ahead and run the All right, so Fibonacci is hit with n is equal to 5. Still n is equal to 5, just continue. But now this is going to call Fibonacci back. The first one we should see is n is equal to 4. So you can see that n is 4 at this point. But now as we keep running this, so now what should we expect to see next? So we're starting out with 5. Let's actually work on that trace really quick. So we're starting out with 5. We know that 5 is going to get split into two calls, right? What are the two calls? 4 and 3. So 5 is going to get split into 4 and 3. Then 4 is going to get further split into 2. That's 3 and 2. And then 3 is going to get split into two calls as well. That's 2 and 1. Right? Make sense? Now, so we have this, and then 3 gets further split down here into 2 and 1. And then 2 gets split into 1 and 0. 2 gets split into 1 and 0. So that's the total number of calls we expect to see. Notice that I did not break 1 further down. Why is that? Why didn't we break down 1? Because it's a termination condition. If n is equal to 1, there is not going to be any decomposition. The way the code is laid out, if n is equal to 1, then you'll actually just return 1. There is no further decomposition. So how many function calls are we talking? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
It's actually 2 more because 2 is.
Oh, that's right. There's a 1 and a 0. So it's 15 calls total. Right? That's how many calls there are. A lot of repetition, clearly. 3 is being called twice. 2 is being called thrice. 1 is actually getting called 1, 2, 3, 4, 5 times, and so on and so forth. So that's the kind of repetition we were talking about last time, that you can actually avoid a little. And this is also one of the curses that comes with recursion, that you do have to be careful. If you're not careful with recursion, you can actually lead to some really suboptimal code here. If we were to take the same Fibonacci and actually implement it as a loop, it's a little more thinking that you have to put in on how the Fibonacci loop is actually going to work. But the reality is that it actually leads to a very simple, it's only going to lead to just 5 iterations of the loop, and that'll be it. But here we are talking 15, and this is for 5. I did not get into 6 because then 6 is going to require, so in fact there is a shortcut way of getting to 6 since we're on the subject. So what if we wanted to do 6? 6 is going to get broken into 5 and 4, right? So we know how many times Fibonacci is going to get called for 4, right? So we can just count these. This will be 14, I believe. So 4 is going to take 14. 5 we know is going to take 15. So with 6, it's 29 times the function is going to get called, and mostly repetitive. How many times do we really need to call it? It's really just 6 times. 6, 5, 4, 3, 2, 1. And for all of these over here, we should just be able to reuse the answer. We shouldn't really have to do the call. Yeah?
4 is going to call Fibonacci 8 times.
4 is going to call 8 times. So 1, that's, okay, yeah, you're probably right. 4, 3, 2. 1, 2, 3, 4, 5, 6, 7. Is it at 9?
It's 8. Oh.
4 itself will be
Oh,
counted.
4 is,
So
it's
9 calls, so that'll be 24. But the message kind of stays the same. The key is that we are clearly being repetitive. We are calculating 4 twice just when we are wanting to deal with 6. And this is one thing that you all never want to forget about recursion is that if you don't, if you're not careful, sometimes the recursive algorithm's so natural and easy to write. I can almost bet that most programmers that you would ask, like how would you develop Fibonacci, will actually give you this solution. This is kind of the most common solution you'll see in textbooks as well for Fibonacci. But it's actually a very inefficient solution because literally everything is being run at least twice, if not more. Now, we did talk about solving this problem a little last time. That's a little beyond 312, but I did want to at least mention what the solution could look like. So the way you would do something like that is, and dare I actually get into that quickly, but I'll just call it I use a term called the memoization table, or MT. I don't want to do is put a. So what you want to, what you can do, and very tempted to just do it, is probably easier to do it than to try to talk through it. So if I did something like this, basically what I've done is created like an array of 100 integers, and so cleared the entire table out, and then pass in the array of integers straight into the Fibonacci function. And I'm going to pass the length of the function as well, so a pointer and the length of the array. So what I'm going to do is I'm going to call this a new function so that later when you guys take a look at it, you know that this is the advanced way of doing it, and it's not to be confused with the other one. So we have 3 values that are actually going in. There is a pointer to an integer array. There is a size. And there is the actual n that is being passed in. So remember that the size is really just the size of the memoization table. So what I'm going to do is I'm going to say if n is equal to 0 or n is equal to 1, return 1. We know that one. No changes there. And just bear with me for a second because the next 2 lines of code are interdependent. It's really hard to write one without the other. I'm just going to say if empty, so I do want to check if n is greater than size, because what I don't want to do is access the array if the size of my n is actually bigger than my memoization table. So if n is greater than the size, then I just want to return the same thing we did last time, which is return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Simple. So if you're looking for a factorial Fibonacci greater than 100, I just said we'll just not deal with memoization. We'll just let you calculate it. It's only for values below 100 where we're going to get a little smarter. In fact, let me pause here. Does the code up till this point make sense? We just added a condition saying, I don't want to mess with the memoization table if n is greater than size. In fact, what I really want to say is n is greater than or equal to size. Now we're going to get into a little bit of a fancy thing over here, which is if, and that could just be an else on this if. Now, can we actually do some memoization to make this smarter? So we can actually check if mt of n minus 1 is greater than 0, and I'll explain this code here in 1 sec. Let me declare a couple of variables here that'll make life a little simpler. Int so just created a couple of global variables to hold the values, and I misspelled this right here, so let me fix that. N minus 1, n minus 2. So what I'm doing here is checking if the memoization table contains a non-zero value for n minus 1, just grab it from the memoization table. If it contains the value 0, which is the else portion, I'm just going to say n minus 1 is equal to Fibonacci of n minus 1. And then I'm going to say, and this is kind of where the magic happens. And I'll actually pause here, and then we'll work through this here in a sec. If m of m minus 1 then is equal to n minus 1. And the reason this is not panning out is because now let's work through this code, because this is kind of a big departure from everything that we've seen so far. So what I'm saying is, remember that when we created the MT stands for the memoization table, we set all of its elements to 0, right? What that means is that if the memoization table, so where is the memoization table getting written in? There's only one place in this code so far where any element in the memoization table is getting updated. That's the line of code right here. Now you're saying memoization of n minus 1, right? That's the only place it's getting written. Now, if there is a non-zero value, what that means is that I have already calculated the Fibonacci of this n minus 1 of this value before. Fair? I've already calculated the value of this. Since I have already calculated the value of this, I do not want to I want to save that value in my memoization table. Remember we talked about how when I say 4 times 4, you guys don't go 1, 2, 3, 4, 1, 2, 3, 4, you just say 16. Because you have that value in your memoization table. It's been memorized. That's exactly what we're doing over here. What we're saying is, I have already calculated the value of some value n minus 1. So I'm going to go ahead and save this value in my scratchpad, my MT. Next time, when there's a call for the same n minus 1, what's going to happen? It would be a non-zero value. The memoization of table of n minus 1 is going to be greater than 0, right? Because if it's the same n, so let's go concrete. Let's say here n was equal to 4, so n minus 1 will be equal to 3. When we are starting out, what is the memoization table element 3? What's the value of that when we are starting out fresh? It's going to be 0 because there's nothing there. When we are starting, everything is 0, which means that your if is not going to be true. You'll hit the else. You will calculate the Fibonacci of 3, and then at the end, we'll save mt of 3 and set it equal to whatever the Fibonacci of 3 was. Now, if next time around when you'll again get n is equal to 4, your mt will be equal to mt of 3. Well, this time it will be non-zero because we updated it the last time you actually came around here. And since this will be equal to 0, we don't need to recall Fibonacci. We will just simply pick the value straight from the memorization table. There is no need to make a function call. Make sense? We do have to do the unfortunate act of doing the same thing for n minus 2. So if mt of n minus 2 is greater than 0, n minus 2 is equal to mt of n minus 2. I'm being a little repetitive here. There's a slightly better way of writing this code, but I think it'll actually come in the way of learning, so we'll just do it this way. So n minus 2 is equal to fib of n minus 2. mt of n minus 2 is equal to n minus 2. So at the end of this code, the first one, the variable n minus 2 is going to contain the value of Fibonacci n minus 1. And at the end of this code, it's going to contain the value of Fibonacci n minus 2. And at this point, we can just simply say return n minus 1 plus n minus 2. So let's go through this code, but this time we will actually execute it because it's a lot easier to see when it's actually being executed. So we've taken care of this. We've taken care of the condition that n is greater than or equal to the size. We just want to not care about the memorization table anymore. And then if memorization table does apply, because we are within the reach, I'm just saying memorization, calculate n minus, if it's in the memorization table, just read it. That's the equivalent of 4 times 4 is equal to 16. If it's in the table because you have done it 20 times, you don't want to do it again. You know the value, just grab it. How do I know that we have done it before? I know it because the value is greater than 0. So if it was 0, that implies that I haven't done it yet, and hence I want to recalculate it. If I haven't done it yet, then I want to do it. But then this is the key. This line is what makes it all come together. But when I calculate it, I do want to make sure that I remember it for next time. So what you don't want to do is 4 times 4. Every time you ask that question, you have to recalculate it. At some point, what you want to do is I just calculated Fibonacci of 4. I want to be sure that I save it in my memorization table so that I don't have to do it again. And then we do the exact same thing with n minus 2. And then you get the final answer. So first of all, before we go further, does the code at a high level make sense? We'll go in and actually insert some breakpoints. So it will hopefully make a lot more sense here in a moment. So let's actually put some breakpoints. And we are going to be running, the first thing we'll run is, so remember that, again, go back to the declaration of empty. We created it. We created it as I used a for loop to set everything to 0. Why was this important? Why couldn't I leave it as non-zero values?
It could be greater than 0.
Because if it's a local variable, it could be greater than 0. What happens if it is greater than 0? What happens to the other piece of code?
Take it as a...
It will just take it as if we have already calculated it, and it'll just grab that value from the memorization table. But this is forcing it to know that at this point, we know nothing about what Fibonacci is going to be doing. When we'll go through this code, Fibonacci MT will be implemented. Remember that this is something where I did the right programming practice. I did a couple of things here which are both very critical. This is not instrumental for getting Fibonacci to work, but I passed in a couple of variables here which are pretty important. One is, rather than putting MT as a global variable, because that's one of those natural mistakes that you could make, instead I actually went ahead and put it as a local variable, cleared it out, and actually passed it in as an argument. And then I passed in the size. The reason I passed in the size because what I want is my Fibonacci empty to be independent of the size. I want to decide the size from outside. The programmer can use it however they want. what I don't want is to have it so that it only works for a given size and not for something else. We did have a couple of mistakes in here, which we should fix. Fibonacci, we were calling from Fibonacci empty, we should be calling Fibonacci empty, so it's the same recursive call. You call that function, it's going to take the same arguments, empty and size. And this, by the way, shows up quite a bit when we're dealing with recursion, where you take the same arguments that are being passed to the parent function and just pass it to the child, recursive calls. Happens a lot, no changes, absolutely no changes here. I'm literally just copy pasting empty and size, empty and size. And I'm going to do that for all other calls to Fibonacci as well. So we are calling it in one place here, we are calling it here, and we are calling it here as well. All right. So let's try to build it and see what happens. What's that? Sorry?
I think you need to restart it.
That's a good. Yeah. I need to stop debugging and then actually start over. And then should probably get rid of these anyways. We are actually going to be looking at Fibonacci empty this time. So let's actually first just go through a quick run and we'll just do a couple of these. Let's actually start debugging. Okay, so here's what things look like. So empty is a pointer, we know that. No big deal there. Remember that we created an array here of size 100. N minus 1, n minus 2 are just local variables. They haven't been initialized yet. We know that n is equal to 5, right? So what do we expect to happen the first time? N is equal to 1 and n is equal to 0 are not going to trigger. So we know that this is going to glance over. Is this going to trigger? N greater than or equal to size. So n's 5, we'll skip this over. But this part will trigger. Will this trigger? N minus, so n is equal to 5, which means we're going to check for empty of 4. What will this if check trigger? It won't. So we actually expect it to come down right here. And then we will actually have a call for empty of 5 getting calculated. And then empty of 4, and then empty of 3, and so on and so forth. So similarly, over here, we are going to see a call for n is equal to 3 happen, because n is equal to 3 is not currently present. But what's interesting is that when we run n is equal to 4, just going back to this picture here, when we run n is equal to 4, it's going to calculate 3 and 2, right? And then 3 will further get split into 2 and 1. When we will actually see empty of 2, this time, this will be a second instantiation of fib empty with n is equal to 2, right? So what's going to happen with the memorization table? It's just going to grab it from the memorization table, and this breakage is not going to happen because it's going to be in the memorization table. It's just going to grab it from there. No computation is going to be necessary because we know we have already calculated 2 once. So far there has been no repetition. We went from 5 to 4 to 3 to 2. We did this 2, and that's going to get taken care of by itself. When you're done with 4, it's going to come down here, and well, actually, and 2 will be skipped again. It's going to come down here. 2 will be skipped again. 1 will be skipped again. In fact, 3 will also be skipped because we've already calculated over here. So at the end of this, we expect to see that out of the 15 times that the function is actually going to get called, only 5 times it's actually going to get, the function will get called. The other 10 times, things will actually start coming back from the memorization table. We'll just go 5, 4, 3, 2, 1. Now the memorization table will have all the values, and I think that's where what we'll do is we'll pause and actually take a look at the memorization table for a second. And after that, everything else will really just get pulled straight out of the memorization table. So just going further with this, so actually what I'd want to do is step into, so as we kind of discussed, it's going to jump straight here. It's going to pass over this if. It's going to jump inside the Fibonacci. That's going to be the recursive call that actually happens. So if I actually do a jump over, and we are starting to recurse. This time n is equal to 4. Since this is the first time we are seeing n is equal to 4, we expect to see that it's actually going to take the same path, and now we will see n is equal to 3. It's actually going to take the same path because n is equal to 2. This is the first time. And then n is equal to 1. It actually just returns from here. And now we are actually going to start seeing some actual progress for our MT. So, all right. Notice how you've actually ended up beyond the if statement this time? Because at this point, MT did actually have so we basically finished the function call. Now the next thing we're going to do is, this is the first time we are really updating the MT. So far, MT has really not been updated. Again, this is going to require a function call. This is just n is equal to 0, so it just goes through straight. N is equal to 2, so now we have updated the MT the second time. Now we have updated the MT. So we have updated the MT for 1 and 2. I think now we just updated it for 3. Oh, I actually missed one of the invocations of it actually working. Now we are actually about to update it for n is equal to 4. So this is interesting now, right? N is equal to 4. What that means is this line of code, MT of 2, right? Have we calculated MT of 2 before? Fibonacci of 2 before? Yes, we have, because we went through 4, 3, 2, 1. We've calculated everything. So this time we should expect to see that it will not actually cause a function call, right? It did not actually cause a function call. It's just going to grab it straight from the memorization table. And we just saved ourselves a function call. So skip over this, go back here. Now it's back to n is equal to 5. We're actually just going to update this. 5 minus 2 is 3. Have we seen that before? Yes, we have. So we're not going to see another call for 3. And we did not. It actually jumped into getting it from the memorization table. Jumped over. And basically back to our answer. Fibonacci of 5 is equal to 8. But the key is that we were able to eliminate pretty much all of these. The only functions that really get called were right here. So since we had talked about it, a couple of students had mentioned in the feedback that they would like to see some examples, and I figured it's actually a good programming construct to have in your tool bag, because you'll be surprised how few people actually understand this concept. It's a very powerful concept. The ability to save an answer from a function call and then just use it next time so you don't have to re-execute the entire function. And this is what can make recursion superior than recursion actually superior than an iterative solution. Because now you have the best of both worlds. By the way, one thing worth noting, and I'll get back to your question in a second. Now you're actually back in main, so you can actually see the contents of the empty array. See the contents of the empty array. Position 0, we have 1, we have 1, we have 2, we have 3, and we have 5. Sequence seems familiar. It's really building up the Fibonacci sequence that is in the empty. So if we ran it for Fibonacci of 100, it would have filled the entire array, which means that now you can actually, any Fibonacci value needed between 0 and 100, you could actually grab it instantly straight from the memorization table. No computation required. So over time, the way you build it, this is actually very analogous to your web browser caching. So ever ran into that where you go to a website and it takes forever to load, and then you go there the next time and it loads instantly on your phone? What happened? Does the website became faster the second time? No, what really happened was that the first time you actually pulled, it actually saved it on your computer. The next time you went to the same address, it just pulled it out of the memorization table. So that's actually the exact same concept. It's the idea of having a memorization table on your computer that actually is the history cache for your web browsers. So you had a question?
Could you just say the Fibonacci of 5 as well at the end before the...
Yeah, we could. And if we later wanted 5, then it'll just come out of it. There's actually several other optimizations we can do and shrink this code as well. My goal is just to kind of give you guys an idea of what I meant when I talked about last time, that you can actually speed recursion up significantly using a memorization mechanism. All right, so let's actually get into the next piece, which is so numerical problems are just one use of recursion, and we will do a lot of that. You will be doing several practice problems on Friday on how you take a problem and break it up into smaller problems through recursion. So to give a few examples beyond just mathematical examples, one of them is that there's sorting algorithms out there. We haven't gone into that in this class yet, but you'll be learning it in 322C. There are sorting algorithms which actually work on this principle. So I have an array that I want to sort. Rather than sorting the entire array, I just divide it into two and sort the left one and sort the right one, and then just merge the result. It actually is a lot faster than actually merging the entire array together. You actually split it up into two, merge, sort the two halves, and then merge it together. That's an example of recursion, for instance. Then I can take those halves and further split them up into two quarters, sort them, and then merge. But the idea is that if you can actually, for recursion, what you need is a decomposition and a termination condition, really. That's all you need. And take a complex problem and turn it into a simpler version of the problem. So I guess this one is best done on the whiteboard. So one of the problems that is usually a pretty interesting one to look at, the length of a linked list. The length of a linked list was on your exam, if I remember correctly, right? So the goal is to get the length of a list. We know that the linked list looks something like this. Is there a way to actually break this problem down, the length of a list, break it down such that we can actually do recursion on top of the linked list to get the length of the list? Any ideas? So my function call that I'm trying to do is, and I'm just going to call it linked. It actually has a node pointer to head.
Using your memorization table?
Let's not worry about the memorization table.
Yeah. Return 1 plus the next node.
So the first, kind of the same mentality, a decomposition and a termination. Let's deal with the termination first because it's easy. What's the termination here? When do I want to finish the recursion?
No.
So when head is equal to null, what would that mean actually, when head is equal to null? So actually, let's talk about that for a second. When head is equal to null, what is the length of the linked list it's pointing to? It's 0 because there is nothing in the linked list when head is equal to 0, right? So we just do return is 0. That's one of our termination conditions. If head is not equal to null, what is the termination? What is the length if head is not equal to 0? So one of you was already saying it, and actually I won't give you guys the answer. So what is the answer? What would the decomposition of this problem look like? It's actually dead simple.
1 plus length.
1 plus length.
Pointer to
Head, which is the head to the next pointer, which is just the next node. And that's it. That's really all it takes to get the length of a linked list with recursion. What we did was we took a problem like we have here for a linked list, and we just said, well, the length of a linked list of this linked list is the same as the length of whatever is besides the first node plus 1, right? We just said, I have the head pointer here. It's one node plus another list which is pointed to by head to the next. That's really what the assumption that we made. So I can decompose the problem and I can say I have a list. I don't care how long it is at this point. All I know is the first node is 1, and then I need 1 plus the length of the rest of the list. And that'll give me an answer to my solution. And then I just have a termination condition saying if head is equal to 0, just go ahead and return 0. And you actually have a solution to the length of a linked list problem. Again, conceptually important to think. What we are really saying is I have a pointer to a node, and what I'm going to do is I'm going to think of it as one node plus a list. The length of the entire list is going to be 1 plus, because that's the node we are pointing to right now, plus the list or the other nodes that are actually pointed to by this node. Make sense? So very, very simple, very clean solution, and requires very little thinking. And one of the nice things about this solution is, and this is kind of the classic mistakes that people tend to make around linked lists, is around termination conditions. What's neat about this is that it actually handles all the corner cases that are typically like the pitfalls around linked lists. So what are the typical corner cases while we're on the subject? When you're writing code around the linked list, what are the cases that you want to be sure that you think about before you start writing your code of a linked list? So one of them is always empty list. Always important to make sure your code is going to handle an empty list. Typically, the other thing you always want to look for is what if you have a linked list of size 1? Because that's critical. That has some special properties because your head to the next is actually equal to 0 right away. And it's actually easy to make that mistake where you come up with an algorithm which cannot handle size 1. And then you have the more general case of size greater than 1, size of 2, size of 3, and so on and so forth. And these 3 lines of code actually take care of all of those cases because we have a solution for an empty list, clearly. If the linked list is of size 1, that means this is what the entire linked list looks like. So head is not 0, skip over this one, and what you're going to get is return 1 plus head to the next. Head to the next is 0. So when the length gets called with 0, it's going to just return 0. You'll get 1 plus 0. The length will be equal to 1. And as we add more lists, it will just continue to scale up and just continue to work. Very simple, very clean solution. Can we apply memorization to this? Let's first start there. If we're talking about, since somebody brought up this point, it's worth kind of arguing through this. If I'm going to calculate the length of a list, can I really apply memorization to it? Because there is no repetition in calculation. I'm going to get a different pointer every time the function is getting called. The whole idea of what makes memorization interesting is that we were calculating Fibonacci of 3 times. We were calculating Fibonacci of 2 4 times. And we thought that that was redundant because why am I calculating the same thing over and over again? In this case, you're really calculating the length of a list. And there's not really repetition. You're just going one node at a time and just keep adding 1 for every node as you go. But 3 lines of code takes care of all the corner cases, just kind of works out of the box. No chance of an error if you do this one right, for example. So that's one example of a non-numerical list. And maybe I will just type the solution out really quick. Especially since this was actually going to complain that we don't really have a head here, so we'll see. And to be accurate, I should define struct node. So a very simple solution to something like get length. And we won't actually write the code for this, but I want to actually go over one quick example, which is a little more involved and actually solves a real world problem. It's actually a rather interesting use case because it's got a new flavor to itself. So, anyone ever played that game where you have to take you have to get the mouse to the cheese or something? Like you typically see those in newspapers. You have a mouse standing in one of the boxes. You have a checker box. Typically, it'll be set up with something like this. I have a checker box, and I have the mouse right here, and I have the cheese right here. Okay, so try to draw the cheese as good as I can. How do you get from here to here? Because some of the boxes in the middle might be shaded. And if a box is shaded, you can't really go through that. Make sense? Seen simple games like this? So let's just create a bit of an example here. So I just want to be sure I don't create one which does not have a solution, because then it's not interesting. Alright, simple solution actually. Go either of these paths, get down here, right? So that's where you're starting, that's where you're ending. Can you actually write a recursive function to solve this problem, to solve the maze? And it's actually one of those things where it's significantly easier to do it with recursion rather than, say, doing it through loops. So there's a few rules to the game. There's a few rules in terms of termination here. The rule is, if I'm standing on something that is actually colored right now, that is actually black, I should not be standing here and I should just return, because that's not the answer. There's another termination rule, which is, if I'm standing at some place where I'm standing on cheese, and done, declare victory. Those are my two termination conditions, which is, if your mouse ends up over here, or if your mouse ends up over here, this case we want to call everything done, success. And in this case, you just want to say oops, and just go back. Fair? Now, so we'll just use a square for the mouse, because it doesn't make sense to have the mouse shaded as well. So you start out here. What are the two choices what are the two different choices that the mouse can go to? So I have here, I have here, I have here. In fact, to keep life simple, let's just exclude diagonal for a second. So two choices. I can go here or I can go here. I know that where I am right now is not cheese. The first thing you want to do is check if where I'm standing is cheese, because that means I declare victory. Not standing on cheese, not standing on a shaded region. Then I have two choices. I can either move here or move here. So I can move, one of the easiest ways to solve something like this is, we just call them north and east. So I can either go south or I can go east. Two possible choices, right? So this is how you can solve something like this with recursion. So make a recursive call, move the mouse over here. But since we have already checked that there is no cheese here, just shade this one up, just like everything else is shaded. Now what this means is, now the mouse is over here. Will it go back? It cannot, because we just shaded before we actually left that place. Is there cheese here? No, it's not. Is it a black spot? No, it's not. Which means that, again, I have two choices. So I can either I look for my choices and I can go here, or I can go here. We did not explore that path yet. We did not go through that exploration. And the reason this example is kind of interesting, because that's exactly how you would do it if you were doing it on a newspaper. Typically, you just go down one path, and when you hit a dead end, you kind of backtrack. So mouse is here. I have two choices. Again, east or south. Say I pick east once again. Same thing I'll do. I'll actually shade, make a recursive call, move the mouse over here. Once it's over here, really only one choice for moving over here. So move over here. Again, I have just shade this guy. Since this guy is shaded and this guy is shaded, there's nothing up there. The only possible position is right here. And we just got here. Now what's going to happen? It's a dead end. You've basically locked yourself in. So the recursion function terminates, shades this one, return, all the way back, and return now has a literal meaning. You've seen this path, you have left your breadcrumbs so that you don't go down the same path again. You'll actually get back to all the way to over here where your mouse is standing again. Again, you have the choice. Now here's the key transition I want to make from the real world into code. Now this, to your computer algorithm, looks like a new chase, or a new maze basically. It's the same game with the same rules, but it really is a new maze to solve. What's the difference between this maze and the maze we started out with?
All those shaded.
This has more additional shaded boxes. So can we turn this into a recursive function? I have a maze, I make some changes to the maze depending on the rules of the game and things that I've seen, and then call solve maze again on this new maze. If that comes back with a solution, you're done. If it does not come back with a solution, then you know that you went down the wrong path, like what happened to us here, and then you start going the other direction. So what the code actually begins to look like, and it's actually surprisingly simple. We won't actually go through all the details, but the code actually begins to look something like, I'm just going to write some pseudocode here in comments. So first of all, we have our termination conditions. If, and actually with the maze, I also need the current position. In fact, anyone has any thoughts on what can we use to represent the maze in this case? Just wearing your programming hat on for a second. It's just a two-dimensional array. Two-dimensional array of integers. So what I can really do is int 2D array, and then I need a current position. What would it take to represent the current position? Two integers, basically, where I am on the column, where I am on the row. So what I should really do is int column, int row. And then really at any given point in time, I just have to call solve maze, shape where I am, call maze for north, west, east, and south. And then just check the termination condition. So the termination condition is if m of column and row and is equal to, we're just going to do some enums here, is equal to black. I just want to return because I did not find a solution down this path. Similarly, if m row is equal to cheese, I want to return 1 because I did find a solution on this path, my two possible terminations. And then if neither of them happen, if it's neither black nor cheese, then for all directions, and the directions are going to be column minus 1, column plus 1, row minus 1, row plus 1, I'm really just going to call solve maze again. So I'm just going to do m of column row is equal to black, basically setting the current block to black, and then simply just calling solve maze again. Now it's a new maze. I just made a change to the maze. So this new maze, it'll be called to solve maze, column plus 1, row. Similarly, solve maze, m, column minus 1, comma row, solve maze, m, column row plus 1, and solve maze, m, column row minus 1.
How can you do row minus 1 or column minus 1?
Because you might get outside the boundaries, right? Yeah, so in fact that will happen with plus 1s as well. So that will be another check that we should add up here, which says if column is greater than max column or something like that, or column is less than 0, return 0, and so on and so forth. But the idea is you can take a problem that's as complex, and we have like a 15-line long solution for this. So we'll talk more about this on Monday. We'll just pick it up here and then move on to the next topic.